So we have discussed all the rotational energy levels of the diatomic molecule, polyatomic molecule, linear and nonlinear molecule, symmetric and asymmetric molecule. So now we are in position to discuss the rotational spectra. So you have to keep in mind that the rotational spectra arises from the transition between the rotational energy state. But there are some uh, condition that only those molecules have rotational spectra which have electric dipole moment. So those molecules which are non-polar, they don't show rotational spectra. However, they do show the rotational spectra when they are uh, during the process of collision. So as we have some selection rules for the transition and atomic physics, so here also we have the selection rules for the um, transition of rotational spectra. So the two selection rules are that delta J must be equal to plus minus 1 and delta K must be equal to 0. So we know that the rotational energies are quite low. So whenever we obtain the rotational spectra, so most of the time that is an absorption spectra, and that involves transition from the lower rotational state to the upper rotational state. For example, from J is equal to J plus 1. Why we take J to J plus 1? Because the selection rules permit only this transition. It should be from J to J plus 1. So if we have a rigid diatomic molecule, this is for the simplicity. We can also write for the non-rigid molecule. So the frequency of the photon that is absorbed during the transition from J to J plus 1 is equal to delta E divided by H. So that is equal to EJ plus 1 minus EJ. So this one, this one. So here, this is the energy of the, this is sorry, the frequency of the photon absorbed when there is a transition from J to J plus 1. Similarly, we can have the difference of frequency between the two photons when the one there is a transition from J plus 1 to J plus 2, and in the other we have transition from J to J plus 1. So we come here. So it means that uh, the 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 frequency line, they are equally spaced. You know that they are independent of the value of J. So here you see that there are different frequencies, so they are exactly uh, uh, separated by the same energy value, and that are equal to 2b divided by h squared. And here we can find the frequency, and this frequency is, and even we can know this one is, for example, the transition from j is equal to 0 to j is equal to 1. The second one is due to transition from j is equal to 1 to j is equal to 2. The third one is from j is equal to 2 to j is equal to 3, and so on. So here we see that the frequency spectrum of the rigid molecule consists of equally spaced line, and the frequency of each line can be measured, and its transition it corresponds to can be ascertained from the sequence of the line. So this is from 0 to 1, this is from 1 to 2, this is from 2 to 3, and so on. Similarly, we can also have the energy gap between the two lines. So this is the gap between the E0 and E1. This is the gap between E1 and E2. This is the gap between. So as we go on toward higher value of J, the gap between the energy go on increasing. So that is can be ascertained from here. Equation number 8, which was given on the previous page, can also be used to measure the bond length of a linear molecule. So here, this is the equation number 8. and from here we can write the moment of inertia is this one, moment of inertia is equal to mu r square, and then r is equal to this one. So now here, if we know the value of the frequency for the particular transition, and as we have seen in the previous slide, so that we can measure that which particular frequency correspond to which particular transition. So putting those values over here, we can find the bond length. For example, in case of the carbon monoxide, when there is a transition from J is equal to 0 to J is equal to 1, so we have a frequency line equal to 1.153 10 to the power 11 hertz. So putting this value just here, and this one is the mm, reduced mass. This is the value of h curve, this is the value of 2 pi, so we are here. So here, this is the bond length of carbon monoxide molecule. So similarly, we can find the bond length of many different molecules just by examining their rotational spectra. So, of course, the centrifugal distortion effect the rotational spectra. So for linear molecule, the spectrum of non-rigid molecule is the same as that of the rigid one, but the lower energy level and closely spaced. So there is the only difference in the small spacing and lower values of the energy. When we talk about the non-linear molecules, so we also have an effect of the another selection rule that is associated with K. So we have two selection rules, one is delta K is equal to 0 and the other is delta J is equal to plus minus 1. So in energy we have the K square. So there are different values J into the J plus 1 values involved. This of course are all positive value in the transition. So K has J plus 1 value, that means there is a splitting of the energy level because of the non-linearity of the molecule. So here we have a spectrum for a non-linear molecule. So this line, for example, this is from J is equal to 0 to J is equal to 1. So this is only one splitting. This is from J is equal to 1 to J is equal to 2. So we have two splitting. This is from J is equal to 2 to J is equal to 3. So the multiplicity is 3. So and so on. So we see that the multiplicity of the splitting of the energy line that is equal to J plus 1. So from this splitting, we can have certain information. For example, if there is splitting, so it means that the molecule is nonlinear. And if there is no splitting, it means that the molecule is linear. So for linear molecule, there is no splitting, and for the nonlinear molecule, we have a splitting like this. And from these number of splitted lines, we can say that which transition involved to this particular energy state. For example, here we have 5 splitting, so this actually corresponds to a transition from J is equal to 4 to J is equal to 5. Here we have 4 splitting, so it is a transition from 3 to 4. So this is all about the rotational spectra of the molecules. In the next lecture, we will talk about the vibrational energy level and then about the vibrational spectra of the molecule. Okay, thank you so much.